so as promised, we'll be looking at a series of laws which govern the behavior of gases. And in each case, we can actually use the kinetic molecular theory to explain these behaviors. And most of these laws can be expressed in the form of a mathematical formula or equation. All right? So the first of these laws is Boyle's law, which talks about the relationship between the pressure and the volume of a gas. And basically, the law stated in words can be expressed this way. For a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure. So basically what that suggests is that there is an inverse relationship between the volume of the gas and the pressure. If the volume increases, then the pressure will decrease proportionally and vice versa. So that's basically the law expressed in words. It can also expressed in another way, where it says here that a fixed amount of gas at a constant temperature, or for a fixed amount of gas at a constant temperature, the product of the pressure and volume is constant. All right? So what this is saying is that if the temperature is fixed and if the amount of gas is fixed, then the product of pressure times volume will be the same. All right? Now, those are two ways of expressing the law in words. We can also express it mathematically. So we can say that pressure times the volume is equal to a constant, or we can say that P initial times V initial, meaning the initial pressure and volume of the gas, will be equal to P final times V final. Or, if you want to, which is the way I normally express it, you can simply express it like this. P1 V1 is equal to P2 V2. All right? So that's basically how we can express the Boyle's law mathematically. All right? Okay, and what I want to show you here is a graphical representation. Let me get back to my pointer mode. A graphical representation of Boyle's law. So the graph to the left shows you the variation of pressure versus volume. And as you can see here, we can see that as the volume increases, the pressure decreases proportionally. So for example, if you start with a pressure of 4.0 atmospheres and the volume is V, then as you reduce, or let me put it this way, as you increase the volume, double the volume actually, from V to 2V, then the pressure is reduced proportionally from 4 to 2 atmospheres. And then if you continue to increase the volume, again doubling it from 2V to 4V, then you see that the pressure is reduced to the same extent from 2.0 atmospheres to 1.0 atmospheres. All right? Now, the plot on the right shows you a different, it's Boyle's law expressed in a different way, because in this case, on the x-axis, you have 1 over P, and on the y-axis, you have the volume. So basically, what you can write down an equation which shows you what that plot will look like. So basically, we know that PV, write it up here, PV is equal to a constant, right? So if we rearrange this to get 1 over P, that is going to be equal to K times V, all right? So basically, the 1 over P here would be plotted on the y-axis, and the V here would be on the x-axis, right? So therefore, if you're familiar with, the plots, the equations for different types of curves, you see that this is in the form of y is equal to mx, where m is the slope, right? In this case, m would be k, x would be v, and y would be 1 over p. And therefore, this is basically the equation of a straight line. As you can see here, it's a straight line, all right? So that shows you another way of graphically representing Boyle's law. Okay, so go back to my pen function. So the next slide is basically an example. In fact, let me go back to, okay. So the question says that you have a balloon with a volume of 4.50 liters at sea level, where the atmospheric pressure is 748 torr, and it says that if you take the balloon to somewhere elevated, the atmospheric pressure will be lower, which would be 557 torr. So the question is, what is the volume, right? The question is asking for the volume of the balloon when the pressure is 557 torr. So Boyle's law is what you'll be using. P1 V1 is equal to P2 V2. And what the question is asking for is V2. So you can rearrange this equation to get V2 is equal to P1 V1 over P2. And all you have to do from here is plug the numbers in. So P1 is the initial pressure, which is 748 torr, times the volume, the initial volume, which is 4.50 liters. And then we divide by the final pressure, which is 557 torr. So the torr units will cancel out. So whatever the answer you get, it will be expressed in liters. Let me get my calculator. 748 times 4.5 divided by 557. And according to my calculations, rounded off to 3/6 figs, this works out to be equal to 6.04 liters. And that's basically how that is done. All right? Okay, so that's an example using Boyle's law. All right, so the next law we're going to talk about is Charles' law. And Charles' law describes the relationship between the temperature of a gas and its volume. And the Charles' law, expressed in words, states that the volume of a fixed amount of gas at a constant pressure is directly proportional to its, and this is very important, it's Kelvin temperature, which is the absolute temperature, all right? So basically, there's a linear relationship that exists between the volume of a gas and the Kelvin temperature, all right? Now, some more things about the Kelvin temperature. We're going to see how we arrive at this particular scale, the Kelvin scale, by talking about this concept of absolute zero, right? Absolute zero is a temperature obtained by extrapolation to zero volume, and I'm going to show you what that looks like graphically. This represents the temperature at which the gas molecules have no energy whatsoever, right? So basically what this is suggesting is that at absolute zero, right, which is absolute zero Kelvin, the molecules will have no vibrational energy, no rotational energy, and no translational energy, right? Basically what that means is that all the particles will just simply collapse into one, what's the word I'm looking for? One unit, so to speak, and the gas itself would have no volume, all right? So absolute zero on the Kelvin scale is the same thing as minus 273.15 degrees Celsius. I'm going to show you what that looks like on a graph shortly. So therefore, the result of that is that 0 Kelvin is equal to that value. And this is the graph that I'm talking about. So let's say you have a gas and you start off with a relatively high volume at a relatively high temperature, and you reduce the temperature and measure the volume with each time you change the temperature. So you're going to get a plot where the volume decreases as the temperature decreases. Now we all know that gases, when you lower the temperature sufficiently, become liquids, right? So therefore, at a certain temperature, and it depends on the boiling point of the particular gas, the temperature will be cold enough to convert the gas to a liquid, and therefore you cannot do any more plots in terms of the change of volume versus temperature because it's not a gas anymore. So if you were to extend the line below the boiling point of the gas such that it cuts the x-axis, then what you'll find is that if the temperature scale that you're using here is the Celsius scale, then it's going to cut the x-axis here at a temperature of minus 273.15 Kelvin. So let me write that here. So, I mean, not Kelvin, degrees Celsius. So here, it cuts it at minus 273.15 degrees Celsius. And this is where the whole absolute zero concept comes in, because basically what this suggests is that if the gas were to exist at low temperatures, then it will collapse into zero volume at this temperature, right? And at that point, the gas particles, as I said before, will have absolutely no kinetic energy whatsoever, all right? So basically what was decided was that this minus 273.15 degrees Celsius would be considered to be equal to 0 Kelvin, right? So basically that's how we ended up with the Kelvin scale, right? So basically, that's a relationship between the Kelvin scale and the Celsius scale. In fact, the mathematical relationship between the Kelvin scale and the Celsius scale is that the temperature in Kelvin is equal to the temperature in Celsius plus 273.15 Kelvin. All right. In fact, the units associated here with the temperature, or multiplied here with the temperature in Celsius, would be Kelvin over degrees Celsius. All right. So that's basically the relationship between the Celsius scale and the Kelvin scale. All right. So that's why we have the Kelvin scale as a result of this plot. Go back to my pointer here. As a result of this plot right here, where you extend the line or extrapolate the line such that it cuts the x-axis, and it cuts it at this point here of minus 273.15 degrees Celsius, which is equal to 0 Kelvin. Okay, so so that's the point being made here. Extrapolation to the lowest possible volume, which is 0 right here, okay? And that would be the 0 Kelvin. All right, so let's talk about, 1 minute here. Oh, one more thing I should say here, and I don't know how I missed it, and that is that mathematically speaking, we can express Charles' law this way. V1 over T1 is equal to V2 over T2, all right? Now, as we said before, the temperature values must be expressed in Kelvin, right? Now, let me just say this. As far as the volume units are concerned, it doesn't matter what the volume units are, as long as the volume units for V1 is the same as the volume units for V2, all right? But the temperature units have to be the same, all right? And that must be Kelvin. Okay, so I needed to say that so that we can look at this example. So this example says, a balloon indoors where the temperature is 27 degrees Celsius has a volume of 2.00 liters. What will its volume be outdoors where the temperature is minus 23 degrees Celsius? So basically, we're going to use the equation I just mentioned. And the question is asking for the second volume, V2. So we can rearrange this to get V2 is equal to V1 over T1 times T2. So V1 is the initial volume, which is 2.00 liters, times T2, which is 27 degrees. But we have to convert the 27 degrees to Kelvin. Now, for all purposes, we're just going to add 273. We don't need to add the 273.15. So basically, this part here would be 27 plus 273.15. And this would be in Kelvin, divided by, actually T2 is actually minus 23. So let me make a correction here. My bad. So let me erase this here and replace it with a 3. So this would be minus 23. So this should be minus 23 here, all right? And then T1 is going to be 27 plus 273 Kelvin. All right? So this part here is going to be equal to 250. In fact, like I said before, we won't be using 0.15 there. And this here, 27 plus 273 will be equal to 300. So let me do that calculation here. So that will be 2 times 250 equals divided by 300. And times 2 liters. Oh, let me do this again. I think I may have 2 times 250 divided by 300. Okay, so the actual answer here, rounded off to 3 sig figs, would be equal to 1.67. Rounded off to 3 sig figs, 1.67. And the answer would be expressed in liters, all right? Okay, so that's basically how that is done. All right, so we're going to stop here for this video, and then the next video I'll be posting will be dealing with Avogadro's law, which talks about the relationship between the moles of a gas and the volume. All right? Until next time.